If you walk through a modern residential neighborhood, you might pass right by one of these quiet gray boxes sitting against a house. This compact unit houses a highly advanced, remarkably efficient miniature power plant. It is home to what is known as a solid oxide fuel cell. Instead of burning gas to create heat and exhaust, it generates electricity directly through a silent chemical reaction. No combustion, no smoke. But the truly fascinating part is how it does this. The core of this technology is made from the exact same material humans have used for thousands of years to bake teacups and plates. It runs on ceramics. To understand how standard clay holds the secret to one of the most efficient clean energy generators on Earth, we have to look closely at how it behaves under extreme heat. If we zoom down into the microscopic world inside the cell, we find a structure resembling a three-layer sandwich. That middle layer is the electrolyte. In a solid oxide fuel cell, this middle section is a dense, solid block of ceramic. At room temperature, the ceramic behaves exactly like a dinner plate. Gases bounce right off it. But when heated up to 1,000 degrees Celsius, the solid wall suddenly opens up, becoming a highly selective gate. This unique ability to allow specific particles to pass right through its solid structure is the foundational mechanic that makes the whole engine work. To generate power, we pump air across the top slice and fuel across the bottom. The glowing ceramic gate acts as a perfect filter, grabbing only oxygen from the air and pulling it straight through, blocking everything else. When crossing oxygen particles reach the bottom, they crash into the fuel, creating water and carbon dioxide. This collision knocks loose electrons. Blocked from returning, they take a detour along an outside wire, creating our usable electrical current. Other types of batteries in low-temperature fuel cells have to use incredibly expensive rare metals, like platinum, to force this chemical reaction to happen. Here, the extreme heat does the heavy lifting for us. That intense heat also makes the system highly flexible. It doesn't need perfectly pure hydrogen to run. It can easily break down a variety of raw fuels, like methane or carbon monoxide, right there inside the cell. The extreme temperature isn't a dangerous side effect. It is a deliberate feature, turning standard ceramic into an efficient, omnivorous power generator. Because the system has to physically heat up to a glowing 1,000 degrees to work, it does have a distinct personality. You cannot flip it on and off quickly like a light switch, but once it gets hot, it prefers to stay hot. It operates like an untiring marathon runner, steadily and silently churning out power 24 hours a day, 7 days a week. That constant, unyielding reliability is why engineers are scaling this technology up into massive commercial units. This diagram shows how they maximize output at industrial scale. The massive leftover heat escaping the ceramic cell isn't wasted. Red arrows show it routed straight into a microgas turbine, spinning it to generate a second electricity stream. By combining the silent chemical reaction with the spinning turbine, the total energy efficiency of the system reaches 85 to 90%. When you are operating critical infrastructure that demands massive, uninterrupted power without burning dirty fuels, like a modern hospital or a sprawling data center, this relentless efficiency makes it the ideal power source. There has always been one major physical barrier. Because the core is made of baked ceramic, it is naturally brittle. It is vulnerable to heavy vibrations, restricting these plants to stationary concrete pads. But material scientists are currently developing new chemical recipes for the ceramic material that drop the required operating temperature all the way down to 300 degrees Celsius. Operating at lower heat drastically reduces the way the material grows and shrinks as it heats up. This makes the ceramic cells much more durable, robust, and cheaper to produce. Once you have a ceramic engine that can survive the bumps and vibrations of travel, you can finally take it off the ground. Engineers are adapting these high-density power plants for heavy-duty ocean transport, replacing the incredibly dirty fuel oil used by cargo ships today. The technology is even being scaled to power next-generation industrial aviation, giving heavy-duty drones flight times that traditional lithium batteries simply cannot match. What started as a quiet box warming water in the backyard is scaling up to power global shipping and commercial infrastructure. And it is all driven by the hidden potential of simple pottery.